Without recording. Okay, so welcome to the 27th of April 2020 Make Club. We were just having a quick chat about problems with life and coronavirus. And as Arman is saying, in Grasshopper for this week assignment, let me open up all your screens too and the chat. Yeah, human UI. With Grasshopper, you can also make interfaces. I already showed you Firefly. Actually, it was the first session of the Make Club. Firefly, okay, Grasshopper. That you can make interfaces and connect to Arduino with inputs and outputs. Actually, this is the website, not this one. But there are other plugins that they are not straightforward to connect to hardware. But as human UI, they create nice interfaces. There is not only this one, but this one writes, for example, to CSV files and other like JSON files, and allows you to create interfaces inside the Grasshopper and Rhino environment. Actually, it hides the Grasshopper and opens up like a full window. I would say that human UI is really nice to create interfaces, but you are always in the Rhino environment. You cannot execute it without it. So actually, it's really powerful, but not as modular or as standalone as other ones. For example, there was a plugin that it was called Spectacles. Spectacles, yeah, that now is inside TT Toolbox. That is from Thorson Tomasetti, that they have developed in this since 2013, and it's quite good in a way that it publishes models and other references with a slider to a browser. It means you can publish interactively browsers. It's similar to the concept of A-frame. Let me try to show you a Spectacles, maybe a YouTube video. The problem is I always found these plugins a little bit buggy, especially Spectacles. But once you get to dominate this little wild horse, it works quite well. So I think maybe it has an online Spectacles. There is a live demo somewhere. Yeah, it's this one. Yeah. So for example, okay, that's why like the sample doesn't work, but somewhere last week I was playing with it because I was publishing some 3D models on browsers. Well, TT Toolbox has now integrated not only Spectacles but also Platypus. And actually, Platypus is another plugin that works through the network. So actually, for example, you can have all the class looking at the same model and working interactively with it. So let's say, imagine as a Grasshopper as a Dropbox environment. Like this is just something like GitLab and Dropbox online for sharing files of Grasshopper environments. Actually, the Platypus works for what it is quite well. And inside the TT Toolbox, the same as human UI, you have Excel's reader listeners. So actually, let's say, for example, you can have I don't know, ESP32 or a Wi-Fi or Bluetooth was a Wi-Fi microcontroller publishing data, for example, of humidity of somewhere, and writing directly to a CSV file. That is something that we will go deeper during the networking. With these plugins, we will be able to read from that CSV data online and actually update geometry or maybe a graph, I don't know, whatever you want to design in the Grasshopper environment. That make it quite nice. And actually has also Galapagos compatibility that we will go a little bit on today, or what is Galapagos, etc. I think I have an example here of a spectacle sample. Let me see if I can. This is the exporter, no? Yeah, and actually you see samples, mesh colored. I think it's this one. This was not today class, but now that I'm here, I think it's nice. So for example, we have this geometry, visualization, output mesh. Basically, we have a mesh and we have color with a gradient. It's quite straightforward. And what it does is decomposes the mesh into a GLTF file that maybe you have never heard about it, but the 3GS library that is an OpenGL toolset 3.gs.
I heard of it. People say it's like the JPEG of 3D files.
Exactly, it's the JPEG of 3D files. That is this format that now is getting the standard. Actually, you never know how to write the name. GLTFL. GLTFL.
You don't need the last L, it's just GLTF.
Okay, so actually it's a ultra compressed three-dimensional format file. And the structure is similar to a point cloud, but this is slightly different. And actually it does in a really, really efficient way. And you can open big, not that big three-dimensional models, because I have tried large one, it doesn't work that well. But it's quite optimized. It's really, really light for three-dimensional files. So this plugin basically decomposes your mesh into that format, and it saves your three-dimensional file as a JSON. That JSON is open through 3GS. And going again to 3GS, the other day you were working with A-frame with Xavi. This is good for creating AR, VR environments. 3GS has a slightly different approach, but it's quite similar on its own. It's not especially for creating environments, but actually to have visualization. It will be something in between P5GS and A-frame. You can make environments, but also you can produce animations. And actually all these are examples of OpenGL animations online. Some of them are lighter, some of them, like actually, you can at the same time modify geometries and they produce in a web format. And it's quite well. You remember the video of Happy, like the 24 hours video song? It was from Pharrell or?
Pharrell.
Yes, no? I don't know if you went to the web page. I don't know if there was a web page that you can hover again and again over the song. Is this one? Yeah, so actually this page is also made with 3GS. So you can make quite complex animations and visualizations with that one. I don't think it's going to be this one. But that web page was a clear example. No, this is not that guy. So you can make three-dimensional spaces or two-dimensional, or also more like VR stuff. It's quite complex. It's complex, but it's really, really powerful. Actually, right now, to turn, I'm rotating with the scroll of my mouse. Other examples could be low poly. This one is good, and you can create kind of games. Oh, actually, this is super nice. I'm gonna just post this so you can play while we are having the class, because it's lovely, this game. The other day I spent like 1 hour playing. So basically you have a mini car. It's going really slow because of the Zoom session. But you can create animation, visualizations, interactivity, and most of the files is JavaScript that are reading CSVs, JSONs, etc. Depends on what you're reading. Not only to have this kind of animations, but for example, the examples of terrains is good. But for example, this is more similar to what A-frame will do. They can do so emulate some physics, geometry, terrain with fog. Actually, this, let's take out the fog. I'm moving with my mouse, and this model is a JSON file actually. And before going to a JSON file, you have a OBJ exporter, I think somewhere here, yeah. That now they have changed it to a more optimized format that is a GLT loader, because this format is much better. So because you can import with texture, with really high complex and reshining textures, more like a render, and still is quite light. I recommend to take a look at these 3Gs. Why I'm explaining the 3Gs? Because this plugin, actually, the spectacles publish the page to a CSV, to using 3Gs libraries. Let me create a folder 0, ultra original. So it's going to save my file here. Okay, and I'm going to check a panel to see the output, if it's doing well or not. Okay, so now we go to the folder. Nothing has been saved. Thank you. Why? Oh my God. So now this is the model that I can load in any 3ds viewer. This is the spectacles selector model, but there was another one that is actually automatically making also the web page. Let me see if I can find that one. Like basic archive properties. Exporter. Sample. Let me actually find it. Maybe I erased it last time. Sorry for not having this ready. I was not expecting actually to teach you this today. But now that we are talking about spectacles viewer. Yeah. So actually, for example, right now I have this 3-dimensional file that I can load another one of the called spectacles file. Where is my file? In this folder. Let's see if it works well. Yeah. And we have a web interface for our model. When the model is really complex, it reduces the quality and it shows you the FPS performance here on the left. And depends if your model is more complex, you can state different backgrounds and ambience to actually create like quite nice models with it. It's interesting in a point. If you want to take more information, just go through the Grasshopper docs, the TT toolbox, and for sure also on the Food for Rhino. don't download the spectacles, download the TT Toolbox. It embeds the newer version. It's quite interesting at some point. Actually, I don't know why I didn't show you the video. Because at the same time, you can start, like, as you are continuously, if you are continuously writing to your JSON file all the time, you can actually kind of semi-publish online the updates if you're reading from your local file. Actually, today we're going to do something similar to this. Let me close this. What is this? Okay, Firefly, no. Let's go. So today, all the files, Marco the other day had problems to download them, so I just zip all the files that we're going to work today in today's class. Is as always in make club Grasshopper class is download link for zip folder for the class script for today, 27/05/2020. So you can download them from there. Close these two tabs. I'm going to also close this. So today, let me close all the windows. I have too many windows as always. We're going to keep going with a last sketch of Kangaroo that I think is quite useful. What we're going to do today is planarization. That is, for example, if we want to build this surface, and this surface is composed of quadrilateral faces, geometrically, any polyline, any triangle is always flat. What happened with more complex and quadrilateral faces? A quadrilateral surface doesn't have to be flat by so. For example, let's just make a plain square surface. We have this surface. I can edit the points. And this face is still a quadrilateral face, but as you see, it's tilted, it's bended by so. What happened? Like a lot of materials cannot bend like this. Metal can do it, but you will need a mold to actually formate it properly. So what happened when you want to fabricate a model, for example, this kind of semi-dome, and you need to use materials that are completely flat. You need to do something that is called planarize, that is transform all these faces into complete planes, like 2D planes, and avoid that the planes are like this. Because before fabrication of this, you will need to discretize this actually model, and you will need to properly fabricate, you will need to cut it in two and have a triangle for here and triangle for here, and it still will not be your shape. It will be an approximation of it. So what we're going to do with Grasshopper is planarize surfaces. This is useful, for example, when you want to create kind of simple shapes that you want to be sure that all the faces are fabricatable. And if you want to go slightly further, you can make it more complex, and you can start adding like overlap frames and things to help you in fabrication. I'm going to show you some images of an example of this coming to life. Actually, I have in my page. I won't show you from there. It's easier. For example, this shape was made out of cardboard, and this is a dome. Basically, well, it's not exactly a dome, it's kind of a tunnel. and you want to be able to fabricate it, you need to be sure that each face is completely planar. And for that, you need to use scripts like these ones to make sure that each face is completely planar and you are able to fabricate with a two-dimensional material, aka also fabricate with, for example, just a two-dimensional cut on a CNC or a laser cut. This is a simple example, and after you just extrude, let's say, as each face is planar, you can extrude as a box each individual face and extract one of the faces and start adding overlaps and the small cutouts, etc., etc. Another example of people that does this is the very many. That is this, but in next level. Because they do this, but with minimal surfaces and discretizing actually not just planes, but also stripes. And they make sure that not each stripe is completely planar, but that each stripe is unfolded in a planar way, because they are using really thin materials. Actually, they use this to fabricate all their installations. Actually, these ones, as you can see, if you zoom in a little bit, this one probably sure is made out of planar elements, but they do this in a more complex way. And after they knit one piece after each other. These images might seem renders, but actually, I assure you that they are not renders. They are real things. So let's go over this, how to create this, okay? Bifocals, I'm gonna hide this. So I'm just going to create a simple dome shape like that one. So I'm just going to create 3 lines. Let me take out this. Okay, I'm going to create 3 simple lines. And I'm going to move one of them in the air. What we're going to do now is, let me move this a little bit. And we're going to input the curves, set multiple curves. And we're going to loft them. So with this, we're going to produce just the surface. Why this happens? Any clue? Because we have drawn the curves in this direction, and the last one, I did the opposite. So what we can do just is flip one of the curves or flip the last one. So we have a simple shape. Actually, it's really ugly. So I'm going to reduce it like this. It's still ugly, but I like it more. And we're going to transform this into a mesh. Let's go for mesh because we want to produce a what? A quadrilateral mesh. If we just transform this loft into a mesh, it will not produce a quadrilateral mesh. It will produce something that matches with the closest approximation that surface. But we don't want to do that. So we're going to use the component that is mesh UV surface. That is going to transform this surface based on some UV values. You remember that when we have a surface, we can use the evaluate component, evaluate surface component, that we can take out a UV point somewhere. It means like, let's say it's a XY coordinate. It's not like that because it's a UV value of the domain of the surface. So in this case, what it wants to establish is actually the subdivision in the U and V values of that surface, in the dimensionality of that surface. So with these ones, we're going to establish the basic subdivision of that surface. Let's see the difference. And now, as you see, we have already our quadrilateral faces. With this, we can just play the subdivision. More subdivision you will have, easier it will be to actually planarize your surface. but also that implies that in cases that you want to fabricate, you will have a really huge and big constraint. That is, you can produce smaller parts and increase your complexity while producing a design or not. In this case, I think this scale will work quite well. Let me reduce a little bit these ones. Actually, what I'm most concerned about is like this kink, because if I have big planes, it will not be able to discretize them and make them planar without actually losing a lot the original shape. Okay, so we have a mesh. Let's assemble the basic toolset of Kangaroo, because we're going to planarize through Kangaroo. What we need to do first is show the model, no? We want to see our model. Okay. What is the next thing we want to do? I'm going to start merging the components. Let's go to Kangaroo. We want to use a component that is called planarize. That is like the strength to make all the faces flat. Actually, I know that this is going to be by default quite high, but I'm going to make it more or less from 10. I'm going to make the maximum 50. Let's just try it like that. We want to also keep the edges length, no? Try to keep the same edge of the faces, no? I don't know if I'm talking alone or...
No, you're not.
We can hear you. Don't worry.
Okay. And actually, this component is going to fight to keep the length of the mesh the same original size. Actually, this component needs to be high. And this one is going to fight for planarizing. But what is another way of planarizing? And actually that helps. Is I'm going to change the color of the visualization so you can see it slightly better. Maybe like this. Let me try. Okay. So actually what we can do is try to make the faces perfect rectangles. So it also helps for fabrication. So if we make a line that doesn't exist between this point and this point, and we try to make the distance between this line and this line, it will help not only to planarize, but also to make the faces quadrilateral, perfect rectangles, and not quadrilaterals like right now. So what we're gonna do for that? We're gonna explode the faces or face extract faces, face normals, deconstruct face. We're gonna deconstruct the faces, but we're gonna explode the mesh first. So actually right now, we not only have one mesh, we have each face is an individual mesh. And we're gonna deconstruct the face. From mesh to face. We cannot mesh explode, so deconstruct the mesh. Okay. We have the face, so we can deconstruct the faces. And we have the 4 points of each face, no? And we have the points for all of them. So we have the point. This is the index. Oh my God.
You can use list item.
Yep. List item. I think last time I didn't do like this. So we want to list the vertices with the index, and we have them. So this point corresponds to, this face has this point on A. This face has this point on A. This point has this face on A, and so on. So we can do the same for the different corners, and that's one of the biggest points of having quadrilateral faces. And what we're going to do is create lines between them. So we create a line not between A and B, because this will happen. We will create a line between A and C. And we will create a line between B and D. And like that, we have already the cross pattern of tension of each one of the faces. Now, what we need to do is try to make these lines equidistant. So it's equal length between these lines. And we merge. Let me see if I forget something else. We need a floor, the plastic anchor. Oh, yes, that's for sure. Clap length, mesh edges, the same. We need the floor, so the model doesn't fly away. Actually, the floor is not mandatory. We can just go with the plastic anchor. That then means like where the model is going to be fixed, or fixed edge is this one, no? Is the floor by itself. How can we extract only the floor? Let's hide everything. So we can use the deconstruct vertices. Let's take out all the points, because they are going to be the anchor points. Okay, we have all these points. How we are sure that we only take the lower ones? One way will be to deconstruct the points, all of them. We know that the minimum Z is going to be 0 and the maximum is something else. No, in this case it's easy because our model is on the ground. Well, but what happens if our model is not on the ground? Let's say here, it's flying, because we are modeling in a little podium and stadium. So in that case, we need to extract the bounds. What is the minimum and the maximum of the Z? And you can deconstruct the domain. So now we know that the minimum is 23.42. Based on that, we're gonna make equivalence. So if the Z is equal to the minimum, tell me yes or no, yes or no. So basically we're gonna dispatch based on the Z level. So we dispatch. We're gonna have the points that are anchored to the floor.
Edu, sorry, dispatch works as if then else.
Sorry?
Dispatch works as a condition, like an if then else.
Yes.
Okay, thanks.
Yes, exactly. It's basically saying true, 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 false. Let's say the condition is if 1, go A, if else, B. You can, in Grasshopper has a tool that is called expression, and you can format and actually write your mathematical expressions also here. That is quite useful. And you have like different rules and operators. If you are more curious about the if then else, there is something that is called NOR, and I think it's in mathematical, yes, operators. That is actually gate and, gate or, gate nor, gate not. This is about making double conditionals. Like if this and this is yes, go do this. If this is yes and this one not, do something. So basically it's like complex conditionals in a way. For example, Fishburne operator. So if this one or this one is yes, just answer me. So it's to actually take more complex components of these ones. It's useful somehow, especially when you work with large data lists. So now that we have set up this point, let's make anchors. and the strength. I don't want that they move at all. Now that we have assembled this, let's flatten and let's assemble the solver. Bouncy solver, button for resetting the solver, Boolean to switch it on, reset, goal objects. I'm going to hide everything. The objects is going to come out here, so I'm going to list item it. And actually, one of the components that is missing in Kangaroo 2 is the planarized show. So for that, we're going to go to Kangaroo 0.99, the other one, because we're going to use this planarity display. This component is going to show us with a color, with a gradient, if the face is flat or is not. So we're going to input the mesh, and it's going to have a base domain and normalize. Okay, we don't need to, and we hide. It was working like this, no? I remember, yes, mesh colors. Sorry guys, today I don't have the day at all. So actually it's showing right now that this Tom has no flat face at all. Really soft and beautiful. What is doing? Right now we have set up all forces to try to planarize, but we have set up any force to try to keep the original shape. That will be the plastic anchors. Plastic anchors are slightly different from a normal anchor. Anchor is meant to be fixed completely in the same position. A plastic anchor will actually take the points. In this case, we don't need to build new ones. Let's show this one. These are the points. We don't need to select all of them. This component has already taken out the ones that we want for have as normal anchor and the ones that we don't want as a plastic anchor. Plastic anchor will be a component that allows the points to move under some restrictions. It means it will make a counteracting force of movement. But if the force is too weak, it will allow some slow movement. In this case, is the limit. What is the limit of maximum movement? So in this case, let's set up, I don't know, actually 10. And let's start the visualization again. That's funny, it's not working. Let me see. The upper one actually was the opposite. Graph. But I don't think this is the problem. Yeah. So actually we have planarized this shape. This is not working at all, so let's increase a little bit the complexity of our domain. And you see now it's slowly, Kangaroo is trying to planarize our shape a little bit. Why this has happened that fast in the moment we have increased the faces? Because before we were having like 10 and 10 more or less, actually like this, and planarizing big quadrilaterals that are huge needs a lot of force, and especially we have a force. Yeah, okay. We have big faces that is difficult to planarize them, and also we are having some forces that are fighting back to keep the original shape. The original shape is this one. So if we want to have this kind of subdivision, we will need to increase the forces to make them work better. In this case, let's not spend like 3 hours making this model. Let's increase the point count. And let's reset the model. So it starts well from the beginning. Actually, it's not working really well. So what I'm going to do is planarize, not planarize at all, and start planarizing in life. What is happening? We have this force that is the equal length that is too high and is breaking up our model. So let's also reduce this force. As I always state, the bad point of Kangaroo is you don't know exactly which values you need to set up. It's about testing and testing. Okay, so by defect, if we don't planarize, we just have plastic anchors and we want to keep the same edge length, actually the model has not changed at all. Let's only play with the sliders of planarizing and edge length. And I'm going to reduce actually and put some decimals to reduce the movements. Maximum 10. Let's go slowly. Okay. It's helping a little bit, but we are still in really low values. Let's go to 50. And let's reduce the edge factor, maybe. Helps a little. And we have a moment it's breaking up. Let's increase the plastic anchor strength. Okay. We have increased too much the plastic anchor strength. Let's reduce it to 50. Changing a little bit. But then again. Whoa. No, it's not liking at all our model. Some shapes are really difficult to planarize if you compare to other ones. No, it's not. It's too much right now. Line strength. Actually, the edge length was not helping too much. So let's start since the beginning. And look at this, we can spend just a whole life just trying to find out the correct values. Let me see what we did last time. Last year, actually, we were looking at the plastic anchor. Our mesh components is the same. We had a floor. We have the points of the floor only. We have these points because we had this shape. Actually, in this case, we were having also the exterior edges because we didn't want to change the exterior edges. That maybe help a lot. And we want to clap the length of all the mesh edges. That clap the length of the mesh edges is the same as edge length. It's exactly the same. Planarize and equal length. Actually, we were having the same. Let me try taking out all the naked points. Naked points are the points that are not inside the mesh. Actually, now it's working much better. Yeah. Okay. So now you see this zone is planarizing in a better way than the other one. Also reducing the edge length helps. Let's try to clap a little bit the length. And exploding 0.5, 0.2, almost there. It's slowly turning green, except for this area. Let's reduce the strength of the plastic anchor. And let's reduce also this one. Boom, exploding. The point of planarize is a component that you need to go from 0 and increase it to make it work in the better way, at the best. Because in the way it works is kind of recursive. We will see what is recursive now. Okay, slowly, 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 and not too much. So we have a force that is fighting too much against. What will be this force? Okay, we have planarized a shape. The dome is ugly as hell. It's a reality. But this could be completely fabricatable. So it's about spending more and more time with it. Actually, last summer I just spent like with the students. We did few of domes like this, and they spent just one day trying to find out the best values for their dome. And this depends also on the scale of your model too. And as you see, the sketch is quite simple on its own, but try to find that the good balance between the models is not that much. Any questions before we jump into another model?
No. So I do now it's completely flat, all the subsurfaces.
All the squares are flat.
Okay.
On their own. Yeah, for example, let me switch off this one so you can see this one. Okay. So for example, this is the same model. Hello?
Yes.
Wait, I'm gonna mute you so you have too much noise in the background. So this is the same model. We have done the things in a slightly different way. We have taken the vertices component, that is a plugin that takes like the points out of your model, but it's the same as deconstructing them. And we have a show component. We have a floor. It's not especially mandatory in this case. And we have extracted the points of the around and the floor in this case. And this is only extracted the floor points. We can extract all of them or just the floor. We have the mesh edges component that can be substituted by edge length. It's the same because this one will measure each individual length of the edge and try to keep it the same stage. In this case, it's the same. We have all the edges and we are measuring them. In this case, we are clapping them. It means we don't want to keep them exactly the same measure, but we want that a maximum they can move 1 to 10% and they can reduce like 15%. Maybe this one helps more than edge length because we are clapping onto a domain constraint and it's helping more. We have the planarized surface. Actually, we have the power of 10. Maybe it's because of this that this was not working. Actually, let's try it out. Let's input some numbers. Plastic anchor and the strength. Power of 10. And of course, now we cannot put 1000. Let's try now. Boom. Actually, look, yeah, a matter of actually using the power of 10. Let's increase also this number because it's breaking up all the edges of the mesh. Let's increase also this one. Almost there. We have lost a few points, but that will be quite easy to fix with increasing the anchor fixing. And actually right now we have the mesh. It was about the power of 10. I was missing that point. So we had the same, and we were measuring the boundary faces. In our case, we have deconstruct the face and take out the points of the face. In this case, it's taking the boundary faces. That is, take out the boundary, check for discontinuity, because if you just take this component, we have each individual square, and discontinuity just finds the discontinuity of the lines. Let's say the points of the polyline, and take out the point. And we were doing the same, crossing A and C and B and D to create the lines that we're crossing. And we were trying to keep them at the same edge length. In the moment you activate, it's exactly the same. Red is not flat. Actually, if with the numbers, you can see the level of flatness between 0 and 0.5, and completely green will be completely fabricatable. Actually, I have tested that most of the material, unless it's not really strong, let's say you have a steel, could be bended a little bit. So around this color is something that you can already fabricate more or less with enough continuity on a human scale. Of course, they will depend on your size of the size. It's not the same making a small hut that making a study, the deviation. Okay, 1 hour just to explain this. Oh my God, today we are going really slow. Cocoon, I think we already explained it last time, no? We went a little bit into it. Just a quick reminder, Cocoon like established influence areas, because we're going to work a little bit with Cocoon and another plugin that is called Biomorpher. So we have some points, and we're going to state that they are attractors between each other. Cocoon, what it does, we can use ground attractors, line attractors in this case, because we were making a line attractor, and a surface attractors like patching. With this, we can create like three-dimensional shapes based on some area of influence about lines, surfaces, and dots. And that will be the radius of charge and the strength of the charge. Longer the radius, bigger that area of influence it is, but the charge also disappears with the size of the radius of the strength. So a really small radius with a really high charge will make a really soft tennis ball, let's say. If you have a really large radius with the same strength, if you have points that are close to the center, they will be attracted, and actually not attracted, they will conform as a geometry, but they're really far away, maybe they don't have enough influence. So those values are always something that you need to play with. And we use the component of bifocals, of Cocoon, that is to assemble like a, let's say, a rough sketch of the three-dimensional shape, and we have a refined component. Today we're going to go and see one more that we didn't saw last time. Actually, we start with, and you see there is a lot of black things. This component we also saw last day, no? You remember? We use a component that is shortest walk. No? Okay, and we went to the point of creating shapes with it. Let's hide this. Whoop. So we were creating shapes out of lines from a structured surface, no? Okay, we have refined the components to make them look more aesthetically pleasing. Like, for example, we can refine them, or we can refine more like we did on the sketch. This is just like minor tweakings to cut them off the floor, etc. Why? Because in this case, let's say this is the support for a table. And we know that the table has to sit on the floor, and we have a piece of glass on the top, no? This is a super fancy, ultra modern design Grasshopper topological optimized table. This really is not topological optimized, but it's a super fancy table that you want to fabricate because you have a big 3D printer, for example. Okay, so let's go for the rules. For establishing some constraints here, we have this box, and we want to establish a base, some base points. The base points needs to be on the base, so they touch the floor, no? And we are setting up how many points? Actually, right now we are setting up like 7 points. So this table can have 7 points. We want to have the dot points. We have built the points with 0. It means the Z could only be in 0. Do we went already for the points? How do we build this kind of points? No, no? Okay. There are different ways of building points. We can construct a point. No, that's quite obvious. We can reference points. We can create random numbers, and with that create points. But what happens when we want to create some really not control or a lot of points? Do you want to create the sliders all the time like this and connect them, all of them, one by one? No, no, it's quite annoying. So you use these components that are called gimpools, bifocals. I don't know if I erased this component before. Bifocals, gimpools. So a gimpool is, let's say, a lot of sliders in one. It's quite useful when you want to create large amount of numbers. And you can set up also what is a gimpool controller, that is like how to actually make sets. For example, we want to have how many number of sliders? Let's say we want to create 30 points. 30 points. 30 points need how many coordinates? X, Y, Z, no? So actually, if we divide this between 3, actually we multiply, we need 90 sliders. Okay, let's create 90 sliders. The domain of the points, it means the range of the movements of the sliders. In this case, let's just keep it between 0 and 100. And we have the decimal, if we want to have decimals or not, and the randomize. Do we want to randomize them? Actually, you can randomize them just with this, or just click randomize 100% by right-clicking. So actually, all the values are randomized. So now we can construct points. We have a point that we have a problem that all the numbers are in a list, in a series. Sorry. They are all together. How we can transform this into points? It's actually a component that is called number to points. And that is going to construct our points. But we have something that we need to set up. What is the mask? Mask is how many points do you want to use? Do do you want to use? For example, if this mask, a mask is X, Y, Z, for example, is I want to use one number for X, one number for Y, one number for Z. So if I put a panel, the first number is going to be actually 74, 4, 68, and the next one, and so on. With the mask, we can just create points in X, for example. And the points will be created just in X. Points. So actually, all the points are just in the X coordinate value. If we change the mask, X, Y, okay, and we have all the points, and the good is we can randomize all the time. Let's say you can randomize the creation of numbers. We will see why this is helpful. It's not only helpful to create large amount of data sets, but also is to use machine learning and topological analysis and some generative design. So we're going to use number 2 points, and this is what we were using here. Is number 2 points, and we deconstruct them to analyze a box, because we have construct the points from in a range from 0 to 1. So based on a box, we want to take points of the box, but only in this phase. One way will be actually not to use domain box. Let's do from scratch actually. I'm going to erase all of this. Suicide. Okay, we erase. Actually, wait, want to see one thing? Yeah, what I was supposed to say. So we have the basic matrix that we have done before. No? Do you remember? This is last day. Let's constrain this into a domain box. Box domain. Or actually it's not box domain, is boundary domain. Boundary volume. It's not boundary volume. Oh my God, today I need a coffee or 5 or 6 coffees.
Hash outline?
No, bounding box. Bounding box. But I want to do it for all the objects. So it makes just a big box container out of it, no? So here we are pretty sure that we want to use only the base and the top. And we want to take points on the top or the base. So what we can do is deconstruct the breadth. Deconstruct the breadth. And we can list each face individually. List item, each face. Right now we don't want that face. Let's put the bifocals. I'm erasing all the time the component. So I'm going to take a slider from 0 to 6 because we have just that one. So I want to take what face? Not that one, not that one, not that one, not that one. I want to take actually the top one. Okay. In the top one, I want to evaluate the surface. So I can only take points that are in that surface. I'm going to do them based on some UV coordinates. No? And for that, I can just use UV masks, a point. What happened? My point needs to be reparameterized. The domain needs to be from 0 to 1, so it's easy to use. So I need to construct a domain, construct domain that is from 0 to 1. Actually, it's good because by default, it's already in that range. We randomize them, actually, and we have right now the values. And right now, why all the points are here? Because from 0 to 1 is here on the surface. What we need to do is scale up and say that this is 0 and this is 1 and this is 0 and this is 1. You remember how that was called? It was called reparameterize. So actually right now we have already all the points of the surface. And like this we can take all the time lot of points. Right now we have so many points. We are making mask of 2 items, no? X and Y. How many points, anchor points we want for a table? Let's say on a glass. Let's have at least 4, no? So actually, let's make a multiplication. And this is going to be the amount of sliders. So actually, right now we have 4. Now we can increase easily the amount of points. And it's going to be changing all the time in our gene pool. Okay, with this, we have the top points, the points to look for. Let's do the same with the base. We have the top. And I'm just going to copy exactly the same. And look for the points on another, sorry. This is the surface. I don't want that surface. I want another one. For the base, I want to take up base 4. That is the base, is the surface I want to evaluate based on these points. And I can randomize and they will be different. Let's say I want to have only 3 points touching the floor or 6 points touching the floor. I have taken the points and I'm finding the closest point. We are finding the closest point of what? We have this original grid and we have looked for discontinuity. It means the points that conform this grid. This grid we can create it with a lot of different ways. We were looking for which are the points that connect one side and the other one. And we were using cross-reference to create the lines that connect them. We find the shortest path and we have our structure. You see the structure right now is, for me, it's quite ugly. Maybe I don't like it. But what happened, for example, if right now I just randomize it? It's taking time, but everything is changing all the time. No? Because we are changing just in a simple click the position of the points at once. That is quite cool. And with this, it's taking a little bit of time because it's actually refining and making everything. Everything was connected behind. Actually, we can erase this part. It's not useful at all. We have the component of cocoon, and we were refining more. Actually, we can also take this one. It's taking too much time. And we were coloring the mesh. Let's switch off everything. So this is our mesh or table. Maybe this is a reverse table, okay? Let's flip it. Okay, much better. So we can do something that is use recursivity to actually produce a lot of models. You have talked, some of you on the MDF have already seen a lot of what is machine learning and these kind of things. Is when you submit models based on some parameters that they will tell the computer if that thing that you are producing is giving a result, one result or another result. But how the computer knows if that result is better or worse is based on a fitness value, usually. And machine learning becomes from having a lot of analysis of fitness values with a lot of inputs Usually, like the minimum to make a machine learning engine, I think Arman knows better than me this part, is have at least 10,000 samples of different scripts. What we're gonna do, as in this case, we're gonna say that we are designers, is we don't want the machine to choose for us. We want to have what is called like big populations of different geometries, and we're gonna tell the computer which ones we like more and we like less. And we're gonna say that between, it's gonna be a mixture of human input and computer input. So we're gonna use a component that is called biomorpher. It's a plugin that I especially like it in the way that the computer doesn't choose for me. You have always the design input, biomorpher. That is basically an evolutionary algorithm. So let's say we have reached this script that produces this shape. Okay, in theory, this script will always work because it cannot get out of the grid size, no? We have constrained the points in a way that they can only be on the grid. But what happened is the point location, we don't control where are the point locations. And actually we don't mind because we have a $1 million 3D printer that will always print whatever we launch on it. So let's say we would just want to have the fanciest shape ever, but we don't want to use too much material. So what will be a thinness value for us? The total amount of volume, no? In this case, we are doing something slightly more complicated, but we can basically say volume to our shape. So the volume of this geometry, that is the total weight in theory of our material of 3D printed, of a pod or 3D printer, will be something that we need to minimize. These scripts work in a way that we input a performance. This will be, the performance will be our thinness, and our thinness will be the volume. Is the number we want to either reduce or maximize. In this case, we want to reduce. We have something that is initial population. So, sorry, I'm not explaining this well, this component. So this evolutionary algorithm, what they will do is they will produce a lot of variations of this automatically. So let's say they will play with the sliders for us. And they're gonna associate each one of the shapes generated with a thinness value. What is the thinness value? The volume for us, because it will be automatically calculated. And it's gonna suggest us a few samples. For example, from 100 populations, it's gonna suggest, okay, these ones are the best ones of your thinness value, but they're gonna look different. And it's gonna show them as these models, and it's gonna say, okay, do you want to keep improving or you want to keep making variation along the similar models of the ones I just gave you? And like this, you can evolve and evolve and evolve and evolve. So for that, we need a geometry. The geometry is easy, is our mesh. We have a performance that is the value of volume, and we have a genome. What is the genome? What is the genome of anything? What is the genome of humans? Guys, it's an open question.
The DNA.
The DNA. And what is the DNA?
The rules.
The rules of how you are made. What are the rules of how this shape is made? The sliders. Actually, it's connecting. Some of them connect the opposite. No, it's connected properly. So, is the position of the points. Varying the position of the points is going to change everything. So it's going to be your genome. It's like if we change a letter in your genome, maybe you have 2 ears, like 3 ears, I don't know. Or like you have 5 legs or something. So just by changing your genome will change everything. So this depends on actually the script you make. And you want to be sure that you have some things that are fixed values and some things that are played around values. Actually, we can transform everything into a gene, all the sliders, but that will be a mess in the point that we don't have anything under control. We want to have at some point flexibility, but sometimes not that much. In this case, I can increase also. In this case, what I can do, guys? Can I input this slider and this slider? No, I can only input this one. Why? Because this slider depends on my mask, and my mask is not changing. But I can change the amount of points that I'm building. That's why I set up a multiplier, because you see I'm changing the points, and it's changing the shape in life. Because right now I have less or more points. In this case, I don't want to change my point count, so I'm not going to change it. I'll randomize them again. Slightly slow. Actually, this is not really good. So this model, what it's going to do is produce a lot of variations of this. The problem of using evolutionary algorithms and let's say topological solvers and everything is you want that your script work as fast as possible. Why? Because let's say this component takes 5 seconds. So if you need to calculate 100 models and each one takes 5 seconds, it's going to take 500 seconds. So you don't want to stay a long time there. So you want to make your script as light as possible. You have seen that I have taken out a lot of things because I want to make it light. Actually, see that my biggest problem is this one here. That is my refinement. And my refinement right now is taking a lot of time. So I'm going to increase it and I'm going to lose quality. I know there is not a big problem. Let's see. Okay, no, maybe this is too much. Okay. Why? Because this is just refinement. It's not determined or geometry. What is determined or geometry is the other part. This is just for visualization and creation of the geometry. So once I have chosen my geometry, I can come here and reduce and increase the refinement. So let's say we have this model. Actually, this subdivision is too much. Let's see if this is not changing anything. And we have a problem right now here. There's something that we didn't realize. You see, right now I have, in some cases, my geometry is making 2 meshes. This is useless. No? Okay, that's a big problem because we are measuring 2 volumes and we have 2 meshes for the biomorpher. We need to somehow tell the program that this is not a valid solution. How we tell the program this? How we can do it? We have a fitness value. Any clue? Okay. First, we're gonna flatten the mesh component, so everything that goes inside biomorpher is gonna be just one. And actually, right now it's inputting just one mesh. In this case, biomorpher works, but we want to establish that if we have 2 meshes or more, it means we're gonna list item. List length. We're gonna say that if we have larger than 1, it's true or false? It's true. We're gonna say that in that case, the volume is infinite. So it's super high. So it will automatically discard it. So for that, we're going to make a power of 10. 1000 of power of 10 is more than infinite, plus infinite, super infinite. And we're going to state that in that case, if it's true, we're going to use a component that is called gate stream. Actually, it's a stream filter. It's filter or gate? I never remember. Stream filter. Yes. It's a stream filter. So if this is stating that is true, this component is going to say true or false. Depends if it's higher or lower than 1. So if it's true, take number 1. So right now the input, the output is infinite. If it's false, take the real volume. So if this is only one mesh, this is going to be false. And by taking false, it's going to take the real volume and output it to the performance. Let's say it's like a gate. Actually, it's a gate. So our rule is going to be, if we have more than one mesh, I don't care about the volume. I just want to input another value. The value to input is infinite. If the mesh is 1, I want to know the real volume. So I'm going to stream it to the component. Okay, so we have already fixed a bug. And we have the genome. We have a performance, and we have a geometry. Initial population is the amount of the samples that it's going to do. So how this component works, let's double click on it. And this menu pops up. So with this, we're going to say, okay, I want to make 100 shapes. And I want to do something, okay. And I don't want to take care, in this case, of the performance. The performance is a value that is gonna show me with each model. And I want to increase the mutation probability. It means, do you want to change a lot of the numbers at the beginning, or you don't want to change them that much? Let's increase a little bit. Actually, we don't need to change that much. And let's go to a random population. It's going to take a few seconds. Actually, it's changing on the back. You see, it's automatically making shapes. It's going to take a little bit if you want to make 100 of them. How was your day? Oh, what?
Was it me? When I opened the microphone, everything disappeared.
No, yeah, it crashed, actually. Yahoo!
I wanted to ask you, why making it infinite means don't take the second mesh? I didn't understand the connection.
Okay, we are feeding to this model. Basically, we're going to associate a model with a volume. No? If the model is not valid, if the model is not valid, it's not valid as a designer, not as a geometrical shape. We can still measure volume. So if we want to, let's say, minimize the volume of a normal shape, what is the against minimizing? Maximizing.
Yeah,
What is the highest? Yeah. What is the largest number that you can use? Infinite. So a way to, we cannot say the problem, hey, I don't like the ones that have two shapes. You cannot say that. You need to establish a rule. And you can do it just by increasing, let's say, the wrong number. The wrong number will be the performance value. The performance value, if the performance value is infinite and you want to minimize, it's like a way to discard it.
No? It's not the reason why it crashed, because it was super big, the value. It's relevant with graph.
No, usually no. It's, I think it was calculating too much.
Okay.
I'm opening again. Luckily, autosave saved me. So we have here, we have the model. I'm gonna hide this. Okay, this is slightly different because it didn't save everything. I think it was yesterday's model. And we have the biomorpher. So let's see if it doesn't crash too much. I'm opening and I'm going to reduce the population size, okay? So we don't get crazy. 50, cross your fingers. So right now it's making random selections. And what is this? What is saying up? Okay, it's a population. Let's say we have Adan and Eva, and you just make one kid. This kid, we have make new kids because they are similar in a way. They are like closer friends, and this kid had 3 kids. So let's say from my initial population of 10, we have make 10 models. Each one of them, we have moved a little bit the values, but not really far away from that model. So actually, this is the population. And what is the proximity between the different models? So right now, this is not something that we can really see as designers, like, oh, I like the one that has a lot of populations. No, you go to designs. Wow, this is different. Now we are talking. Let me make it bigger. So actually, these are the different models, and we can do different things. And now what is this number? This number actually is the performance value. Right now, we were not using the performance value. In an initial population, we don't use it. We can use it now. Minimize. So from now on, I think that, for example, I like this geometry, and I like this geometry. So now I have stated that I like this geometry and this one. The computer doesn't know why I like them. For it, or for the computer, it knows that around those numbers, I have preference. Around the numbers that have created this population, I like them more, and I prefer to evolve from points that are closer to the ones that create this geometry. But I have another input, that is the performance. I want to minimize, and I want to minimize the volume. So what I'm going to do now is create a second generation. So you click evolve. Let's see if it doesn't take too much time. I don't know why I make this huge, actually, because now we don't see the evolving. It's thinking on the back. Can I exit? No. Okay, I just closed it. Let's open it again. History, it didn't keep track of it. Okay, let's evolve less models. Go random, please. Yalla. So I'm going to say that I like, I don't know, this design and this design. And I want to minimize, and I want to evolve. So now it's making evolutions based on those initial population, in that initial population. So it's going to keep similar models. And how it keeps similar models? By having the sliders in close numbers to that models, to the ones that generated that models. And it's also minimizing because it has a performance value that is this one. So actually this is my new generation. And in this case, these models are difficult to see because they are complex, but they will start looking each time actually similar and similar to each other. For example, if I choose this one that are already similar, and maybe this one that is already similar, and I keep evolving. So if you do this infinite times, it will slowly show you less options or options with smaller variations because it's closing up each time. Which numbers do you like it more or less? So it's evolving again. And in the population is telling me, for example, here I have the initial population and which models I like it. And which models am I evolving? And it's taking up the performance value also. So it's something that I can choose as designer. So let's evolve from this one only, generation. And like this, we can keep the whole day just playing with it. So, yes?
Values we could give instead of volume.
Sorry?
I'm wondering how far we can take it, like instead of volume, how you can describe a design that you like with what other qualities.
Actually, this is about how you manage performance. And in this case, the biomorpher takes, you can put several performance. You can put a volume, for example. You can put the amount of points. If you put the sliders, you can set up that I want to minimize the number of touching points. That could be another performance value. You can set up also that I want to have the minimum or the maximum amount of what. For example, we can measure also this. The minimum amount of the maximum amount of connections. For example, one will be, I want to minimize the number of points, but I want to maximize the amount of polylines, individual polylines, because I want to make the design look more complex. You have a problem in the moment you use something like Galapagos. What is Galapagos? That is not exactly the same because this one is done in a different way. For example, Galapagos is not visual and it's not exactly the same, but could be done also with performance. So for example, let's say we want to know what is the volume or what is the geometry, and with the lower amount of volume. We don't care at all about how it looks physically, okay? We just want to know the lower amount of volume. Galapagos is faster, but we want to minimize the amount of volume. So it's going to try and do it the same, but much faster. In general, well, actually, right now it's not going to be fast because it's taking the script takes a lot of time because we want to maximize. We have a visual model. Actually, let's close this. So we want to minimize, and we want to start the solver. So you see, it's gonna do not display the changes. It's taking time, but right now it's calculating everything in the back just based on a performance value. the performance value is or volume right now. Another option will be, for example, I want to maximize the number of points and minimize the volume, but I want that the number of points takes higher percentage of importance than the volume. So in that case, you can join those numbers, for example, by then making them a percentage. So number of points is 0.5% of 1, and volume is 50% of the score. So you can join them by percentage and just give one value as example. And you can vary this by using percentage. So when you have more complex models, you will need to do this with percentages, because you will have a lot of performance data and fitness values. Actually, it's not doing it because it's super slow, this script. Let me try to find, I think we have something here. From Hinder to Cocoon Introduction to Evolutionary Algorithm. Yes, this one. That is what I wanted to introduce now. This is simpler. So, for example, we have this shape, no? We have created this shape. Let's gonna do a simple example. We want to ship this shape. We have this shape fabricated, and we want to ship it, and we want to find a box that takes the less amount of volume. So it's the smaller as possible, and it's gonna be cheaper to sell, to send, because each square centimeter costs us like 50 euros. We want to optimize the box of the boundary box of this. So if you just put it in a standard box, a bounding box, you see there is a lot of leftover space, no? Okay, what happened is the box that is here, let me hide this, is this box, we can make it in a normal plane that is a bounding box. By defect is done in a XY plane, but we can twist the plane so we can have factor of rotation of the plane. So actually we can, let's say, make a box in any direction. By making a box in any direction, we can fit, oh my God. We can fit, basically we are rotating the box to see which one works. Actually, we are rotating the box, and all these boxes contain or shape. Depends on how we put the geometry inside the box. So we have basically 3 sliders to allow to rotate the box around. What is the performance value here? The volume, no? So let's calculate it. I want to save my money. So minimize the volume, start solving. These 3 points is I want to show all the results. I just want to show the best results. And this one is I only want to show the best results. So this one is going to start solving. You see, it's testing really fast. And now it's making the graph. So it's getting to know which values works the best. And by making work these values, the ones that work the best is these ones, actually, the ones that get better performance is going to try numbers closer to those numbers. So actually you see that slowly is making less changes, but just like more refinement of the shape. And definitely you cannot stop laughing. But this is just to ship your 3D printed shape. But this could be done for everything. And actually, you have seen here that has taken a bad decision. It was getting to the best value and suddenly start testing new numbers, and it was getting bad values, worse values, because it was maximizing the shape. So actually, right now it's evolving and trying each time new possibilities based on the new results. So this is it's called evolutionary solvers, and it's for optimization. And depends, this kind of things, you can test it sometimes for a few hours, or it can take like 1 minute. these solvers, if you recalculate them, depends on your model, but they might not give you the same solution. Why? Because they initially make like a number here, a number here, and a number here, and a number here. And they say, okay, I have 5 numbers. Which one has given me the best value? This one. Okay, from this one, I'm going to make variations. So actually, what is called the initial population makes a big difference, because it's going to determine in which direction your solver is going to go. As you see, it's finding better and worse solutions, but actually this is the performance value. And we see that there is almost no change between the top numbers. Actually, let's put it in speed mode. That is not showing me anything. It's calculating faster. That right now, between the first one and the second one, there is only like 1,000, I don't know, it's square cubic millimeters of change. So right now it's evolving on the background, and actually it just stopped it right now. So this range state, it means select that one. You see, I can select which one I want to choose. Of course, in this case, I want to save money. So this is the best solution for this. So this one is the smaller box to ship my geometry. Super silly. Yes. But this is evolutionary algorithm, and this works in a lot of different ways. For example, we can have this geometry. I have these initial points, and I know that I want to have 26 points. I want to make, 15 points, because I have 15 genomes. I can only change it. So this is going to sort. It means it's going to make these points are not in order. This is not 1, 2, 3, 4. This is actually randomly points creation. So I want them to make just a polyline, and I want that the polyline is the shortest walk, let's say, for example. But I want that it's the shortest walk and use all the points, because shortest walk will select from one zone to another one without taking all the points into account. So I want to make the shortest polyline based on all the points. What is the thickness? The length. What is how we're going to sort my points? By changing the sorting list. That is like ordering my list. This component orders the list based on a key value. That basically is an index. So how we can solve this? With evolutionary algorithms, I want to minimize it, star solver. This case is like we have an evolutionary solver and an alien solver. I usually use a evolutionary one. So actually right now it's testing a lot of solutions and slowly getting to the shortest path between all the positions. You can extrapolate this, for example. How you think Amazon, for example, deliver all the packages? By making this, let's say it's not like that, because it takes more things into account, but it takes what is the minimum distance, take the less amount of time by still going through all the points on a city. You can extrapolate this to different things. Slowly finding out the solutions, speeding up. Let's stop the solver and let's just reinstate this one. So actually right now, the shortest path is, which one? This one? Huh? Why we have two? Actually, it's this one. Between all the points. Here we have a gradient to show it better. So this is the shorter cost that goes through all the points with the less amount of distance. But as I said before, this depends on the initial population. Sometimes you need to recalculate a few times this to get actually to a good solution. In these evolutionary solvers, most of the times you have like the population. For example, I want to have a population of 200. So of course it will take more time because it will have to calculate more at the beginning. But we have something that is important, that is the runtime limit. It means if this keeps going for longer than 1 or 2 hours, it means it's not getting to a proper solution. So you need to restart it since the beginning, because maybe if your population is 5 and none of the initial population is good enough, it's gonna have taken, like, let's say, a wrong solution since the beginning, and it's just doing loops in the same procedure. Yes? No? Hello? I'm really alone this class.
Hi.
No, Eduardo.
We can do this with so many things. It's unbelievable. For example, in this case, it's slightly different. We have this. We have this that is like, I don't know how to say. This is a metal bar, and we want to make a catenary between it, but we need to always catch these 3 points. Let's say it's a rope that is hanging out from a roof. I can attach my rope into any part of the roof. I can just move the sliders of my roof. For example, I can do this. But I need to also connect these 3 points, and I will do it with different lines. So, which is the catenary that catches from the roof and matches 3 points? Initially, it's not that easy to make, because a catenary you don't control by matching 3 points. So we can measure the distance, these distances, and this is of fitness value. So actually, please make the catenary that matches, that is attached to the roof and matches these 3 points. This is going to be super fast to solve. But this testing is still a lot of solutions, because the computer doesn't know exactly which one is better than other ones. Initially, the only thing that it needs to know is the performance. If the performance is by minimizing the distance, and you see that really fast is reaching the perfect solution. In the options that you play with, you can also state limits. Let's say when the solution hasn't changed more than, let's say, 1%, stop, because you are not making enough variations. So in this case, actually, it's getting all the time to really close similarities. And right now we're speeding up. And each time the solution is better. And you see that suddenly is making something weird, because between each population and each evolution is randomly throwing some other values, not close to the ones that is working with. Why? To just in case the values that is working with are not the best ones, but is still focusing on those ones, is making a trial completely blind, trying different values to see if it's better by any chance than the one it's working with right now. So it's like you are a handwriter all the time. All your life you have been handwriting without never doubting of it. And suddenly one day you say, okay, I'm going to try with my left hand. And with your left hand, you are Shakespeare. You will not know if you didn't try. So actually the evolutionary solver is trying kind of something similar to see if, but somehow it's doing it wrong. Well, we can keep evolving, usually like a lot of time. I think the time limit is 1 hour. But these are 3 super simple examples, and actually it was not that good that we started with this one because it's quite more complex. But this is, for example, something that you can reach with. You can reach by just optimizing values, and you can use, for example, biomorpher if you want to be also be influenced by the aesthetics, because it's going to show you the result, and you can choose and evolve from them. Actually 6:10 right now, and from finding new biomorpher, from finding space recursivity. There is something that I want to, in the folder I have uploaded a lot of things, and today is space filling, I will explain next day, but I want to introduce to topological analysis. Do you know what is topological analysis? Okay, it's quite simple. Yes?
Isn't it the one that you showed us, Edu, the smallest volume? No?
No, this is evolutionary solvers, but topological analysis works quite similar in the concept. Let's see what it is. Open file. Yes. But it does from a structural point of view. I'm going to show you just an example for this, because the other one is really complex. Actually, no, I'm going to show you the result, but we're going to calculate the example because it takes so much time to calculate the final one. So, for example, this is the complex. Open. What is this? This is a topological optimized drone frame. It's missing a part here for holding the motors, but this is, in theory, this is the most optimized, structurally wise geometry that resists the charge of the motors, impacts, and have space for holding your devices. How we calculate this? Topological analysis is a material structural analysis that you do based on some constraints. For example, in this case, the constraint is my drone can occupy a maximum of this volume. This is the maximum volume that I can occupy. I need to have 4 spots for sure, because I need to place my motors here. So I need to have volume here, yes or yes. You set up other constraints, like for example, I will have something here inside my volume that is going to be heavy. So it's going to be loads. So you establish volumes that you have loads. It means you're going to push force. Let's say the example of the table that we have right now. But in here, we don't generate the geometry. We just establish the rules. We say that this is a support and this is going to be a load. And this is the maximum volume that I can have. So based on that, I'm going to set up other things like material properties, because in here we have performance, and the performance is going to be based on material properties. So for material properties, we have the target density, a Young and Poisson modulus. This will depend on the material. This, for example, is plastic. So I want to use what? 0.5% of the total volume. So what I want to minimize, what is? The total amount of material. But what are my rules? My rules are much more complex. That's something that we can handle just in like 5-minute class. But luckily, topological analysis programs does this kind of things for us. And the things that we need to input is actually what are material properties. So, for example, let's say, look at the webcam. For the program, it knows that this is a paper. It knows that paper works really well at tension, but works really bad at compression. So with this, it can make some equations on how to actually put the material in the model. So let's say the program is going to start with all the material and slowly take out material until it finds the correct solution. Does it look similar to what we were doing? It's actually evolving.
Yes.
It's taking material out and testing solutions. If the solution was wrong, comes back a little bit and starts leaking it out in another zone, let's say. That is the difference between generative design and topological design. Topological design starts from a block of something virtually and takes out material. Generative design is the opposite. It's what we're doing before. We generate the shape based on some performance values. So actually, generative design is not exactly what we did before, but it's the closer approximation. There are not that many, actually, as far as I know, there is no generative design as for structurally wise for Grasshopper at its own, like Fusion has, but and more complex programs, but Grasshopper there is no equivalent. We always do topological analysis. So based on that, we establish a volume and the program gives us a result and does this by evolutionary solvers. This model took like 4 hours to calculate, so we are not going to do it now. We're going to open the simple one.
Which plugin is it, Edu? This one?
This is Topos. There are different plugins for doing this in Grasshopper. Topos works really well if you have a CUDA compatible GPU, like graphic card. But there is another one that if you don't have a really good computer, you can install Ameba that does everything on the cloud. And it's simpler to use somehow. But it can do it also like it's for structurally looking, this kind of plugins. So they have like performance, they tell the material, they tell where are the stresses. Ameba is quite good, but it's cloud that some people, like for example, I don't like especially that it's cloud, but of course it's faster. So let's see Topos. Actually, I see it's missing. I'm missing the plugin, a part of the plugin. So in this case, we're gonna set up Geo. Sorry, it's here. Torus. So Torus is 1. Sorry, need to switch up this and this. So let's say we have this volume and this is a donut and I'm pushing in the top part and I have to support the lower zone. So what is the only material that I need to actually support this? In this case, when we need to set up is a set of rules. So what is the domain? The domain is the donut, is the maximum, the model cannot get out of this volume. I need to set up what? vertical loads. In this case, it's surface loads. The load is going to be the top. Sorry, it's this one. I have a positive load of 100 newtons. It's pushing up. And I need a support. Where is the support? Here. So this is where my model is touching the floor, only this area. I need to set up, this is what is called the constraints, the conditions, the load and the support. And I have to set up also what is the properties of my domain. Let's say what is my material. My volume is a donut, and this volume is made out of this young Pascal is kind of a pseudoplastic. And I want to use a 15% of this volume only. I need to assemble this into a model. That is the model data, that is model creation, model. For the model, I need to set up a boundary condition, boundary domain, boundary condition, maybe properties. In this case, we don't want to set up extra properties, and we need to set up a resolution. What is the resolution? In three-dimensional topological analysis, to make it faster, we work with voxels. So actually, we need to set up voxels inside this shape. More boxes, let's say it's more definition. Basically, it's a three-dimensional pixel. But also more voxels means slower to calculate. So this is the engine. Like if we are assembling the model and we want to calculate it. And this is, let's say, as the same as the kangaroo model. We have Optimus parameters that just by default won't work really well, and the solver. The solver is going to do something that is the optimization process. And here we're going to see how it's going to slowly increase the curve that is making evolutions from the last model. It's much better to see in live, you will see. And basically we can calculate. This usually is slower, so I'm going to only switch off what I need. Switch on what I need. That is the dense preview. Okay, and hide everything. So for example, here you can see actually we are not seeing the voxels, we just see like point clouds. We see this is the model. These are the forces, and these are the supports. And you're going to see how the computer is going to slowly show me the evolution. And usually you will see how the white zones are the zones that are not in use, and the black zones are the zones that have the highest load, the ones that the material is at the most usage out of it. And the optimization solver is saying, okay, obviously, if you start with the volume completely full, your first solution is going to be better than the last one if you take just a little bit of material. So you see that each time actually it's really going really slow. So I'm going to stop it. Okay, I'm going to start again with lower resolution. Resolution 20. You see the, okay, it's too much. I think 20 is going to be fast enough. So it's going to take material and see if that was good enough or not. Actually, it's not going to work because we have this image disappear the supports. And I'm going to crash it. I didn't realize it. Oh, luckily, okay. If there is sometimes, because we are basing our models on voxels, if those ones are not big enough, they don't take well the supports or some zones like that. So actually, I'm going to draw another breadth. It's slightly larger. It needs to be a mesh. So it's red. geo, set geometry, and mesh breadth. Because is the support. Okay, so now it's taking the support properly. Actually, we have a much larger zone of support, more than we actually need. So I'm going to reduce it to here. And let's calculate. You see, it's solving, and each time it's finding more problems to take material out without compromising the shape. Of course, right now we have a big blob because this shape, we have really big pixels. But we have the ISO value, that is the ISO preview. That is the percentage of actually material that we can see from 0.0 to 1. So actually, for example, we can see that this is the shortest path, let's say, three-dimensionally and structurally wise, based on our material for this shape. Obviously, we are working with really big pixels. And this is just a point cloud aesthetics. But for example, we can see with like this, that we see the model, we see the charge loads. For example, we see the higher stresses in blue and the lower stresses in red. And we can also see, for example, mesh previews. Actually, this will be the final result for our shape. Of course, the resolution that we are working right now is awful, as it's not a good model. So let's try with increasing the resolution. Even so, it takes more time. We don't have too much. It was 30 before, no? 35 or 45.
It was 45.
45. Okay, let's go to 40. Actually, it's usually a small change. Okay, I think it's gonna be more than enough. Okay, let's hope it doesn't take too much time but we will see in live in a much better way. This. Okay, 2.5 seconds, not that bad.
And Edu, what about the material of this shape?
The material is done by the Pascal modulus. That is one way of measuring the strength of materials, and the Poisson modulus. The Poisson modulus is kind of flexibility wise of a material. You have charts of this, but I think most of the materials, let's say, if this is in general terms, but in the Wikipedia you can find the Poisson model of the materials and Pascal modulus. You have other problems like, for example, millipede and monolith does the same as this. Monolith is not only for this kind of analysis, it's also for multi-material 3D printing, but has a zone of structural topological analysis. And I think monolith has a material library. I'm not completely sure.
Yeah, it does have, and also you can build like based on some properties, your own material.
Yeah, you also can do in most of the topological softwares allows you to do this, like Topos 2. But monolith is quite more complex than this one. It's, at least all the time that I tried, I found it. So right now it keep optimizing, reducing material. And right now we see that this is actually a lot of material. So we have the ISO value that is actually another percentage of the material that we want to actually use. So we can increase the ISO value and, for example, reduce to only take this zone of material. Let's see what happens when we use a higher ISO. So actually that will be the most optimized shape. This doesn't have to be beautiful. This is the most performative structure to accomplish the goal between this and translate all the loads between them. The mesh component, usually I don't like it too much. So what I usually do is take out the voxels. There is a component for voxels. Solvers, analyze model data, voxel mesh. On most of the programs, ISO. I take the voxel model, and what I do is put it in Dendro or Cocoon, and from those one start rebuilding the mesh again. So it's better in general, because the mesh builder actually does from the voxels, and as you see, the voxel ones is a turtle. Yes. I'm lost right now. So you can take out the voxels, or you can take the mesh and work from there. But for example, this, why we don't, because it's in green. So in here, we can see the different types of stresses by colors, by points, and by range. So this gives us the simple way. This gives us the load by zones, and this actually, I don't know that one. And this model, this other model, gives us proper structural analysis tools. It means where are all actually the stresses, the bond magnitude stresses, the stress values as a vectors. So actually, if you zoom in, it's sometimes kind of difficult to see, but you see the crosses that actually the bond misses stresses, the linear stresses. It means in which directions the forces are pointing to, what kind of stress it is. Is it a linear stress, or is a torque stress, torsion stress, etc. So in here we have all the type of stresses shown up. With this, actually, this model, if you know how to remove from group, you can work with this automatically. Why? How Cocoon works. Let's say we have P stress colors. This is a line. This is a line. Longer the line is going to be determined by the vector, the plane and the vector. The vector has a length. The length, you can make it a line. It's a line vector. Longer the line, more stress. Longer the line, it means this line needs to have more zone of influence, because structurally wise, you need to build around it. So you can start making equivalences also between these stresses. And actually, for example, Millipede is a plugin that right now is quite old, but it still works well, especially for 2D. For 3D is awful. Works like this. You create amoeba millipede here. This video is super old. But... So it basically does the same, but just it creates the lines of the stresses. And what you do is use Cocoon on the brand or a voxel modelizer for stresses to generate the shape. Millipede now has been changed by Monolith. That is really good. But Monolith, but at the same time is super complex to use. Super complex. Every time I use it, I find a lot of troubles to know what I'm doing. Monolith is especially designed to do what is here? It's multi-material 3D printing. That means structures. Daniel, if you remember, it was the GSD of Harvard GSD. Yes, no? Harvard GSD multi-material printing. How is called the School of Design of Harvard? Ah, yes, here.
Yeah, I think you have it right.
Yes. So basically, you want is for printers that can have multiple materials and you can print with. For example, the blue one in this case is a much stronger material, but of course it's more expensive. Let's say it's more expensive and it's heavier. You want to use the lighter chair possible, but if you only print the blue one, it's going to be an impossible to sit chair. So you want to use multi-material to have the benefit of both worlds. So actually, how you benefit one model from the other one? You can topological analyze your shape and keep only the areas of a structure that you need and where you need them. And if you have a multi-material printer, you can print like this. If not, you will finish with shapes like this. That is not that bad, but actually there is a lot of ways to overcome these kind of issues. Like you can print not only with a multi-material printer that is usually a half-meter turtle, but you can offer different types of things. For example, I'm going to show you an example. Hello. I think I have here topological table. I don't know if I have videos of it, but so display.
Can we do it too with the printers and with the robots that we have in IAC?
Multi-material printing? No. I'm sorry. I wish. I don't know if I have the model out of it. So this is something that we started with Ardeshir, that Arman knows. Actually, we were printing how to print this kind of shapes. Sorry, this one. This kind of shapes with a normal 3D printer. For example, this is the leg of a table, a standoff. This is if you have a more or less a circle, a cylinder, just an empty cylinder, let's say a pipe, not a cylinder, I'm sorry. This is the topological analysis for concrete, based on the values of concrete. How the hell you 3D print this if you don't have a $1 machine, $1 million machine? So actually we come out the solution, okay, this started with just a shell, a simple shell. What happened if you embed your model in your shell again? You come up with, look at the camera, things like this. So the model, you have the topological analysis and you have the shell. And it's working as an envelope. Imagine that you drop a drape around the object and you drop another one since the beginning. So actually you can print with just one line, you make the interior, you make the exterior, and you keep it up to the next one. So actually you can print really complex, I don't know if you see with the camera, really complex geometries that you can after fill in with your material. So actually you don't need to print concrete. What you do is a lost formwork where you can cast your material and use the plastic that is printed in just one single shell to use it at a lost formwork, just to contain and to make your material printable, your shape printable.
So if I understood it right, Edu, this is the mold, and you put the concrete inside this mold.
Exactly. So making the mold, printing this in concrete is impossible unless you have a powder printer, something that you can support the material. In fabrication wise, this is super complex. Like it's like you need a lot of resources to fabricate this. How you can decrease this? You can use it to, for example, make a mold. And the mold, it will be in this case is the drop that keeps the holes for filling, but you have still the shape contained. Let's say at some point, if you want, you can cut this one and take out the mold. You can break the plastic. In this case, let's say that's not what's not the idea, but to make it look cool. We started with this. This is what I'm just showing you is a smaller model. Well, talking about Ardeshir. This is Ardeshir. I think we have a few pictures here. Media. No. We have really bad photos of this one, as always. Will I be print? Let's photos. Maybe around here, yeah. We were printing this in big, in huge, in the robot, actually. Let me see. Where are the pictures? Because we start filling, it was transparent. Let me see here. We printed with transparent plastic. I don't know where are the pictures, guys. I'm sorry. A shame.
We need something for the next time.
Yeah. Well, I will try to find out for the pictures. Ah, you are here, Magdalena. I think I can show you in the phone. I have it in the camera. Videos. My collections. Huh? Picture? Oh my God. Wait a moment. Oh, the class is almost over, so. What is this? Here. So we were not only doing a more complex shape, but you can see that we already start casting concrete. We start filling up the holes. We don't see it really well because this is a large image. Maybe here we can see it better. So actually we start filling up and throwing the concrete out, so it was actually feeling like the pouch made by the plastic. Unluckily, this project never finished. We ran out of time. Look, here we can see a little bit. Here was the first two layers that they were together and they split up to make the pocket, and they continue later. So topological analysis is nice. And actually, this three-dimensionally wise is complex to fabricate. I can lie to you, like, is this, or you have really expensive equipment, or you try to find clever solutions, or you print your shape with millions of supports to actually printable. Like, this is printable, of course, but you just need a lot of supports. Unless, for example, you take care that this angle never gets lower than 50 degrees, etc., etc. But making 2D applications of it is easy. I'm going for a 3D printed part. For example, what is the perfect shape of a beam? For example, for 3D printed plastic, if you make a topological analysis in 2D, it's easy because 2D you can always extrude it in line. So you can print it like this and just rotate it. So for example, this beam is taking out these supports and just a center load in the center. So making two-dimensional analysis, topological two-dimensional analysis is easy because we can always FDM 3D print it in an easy way.
What do you mean two-dimensional, Edu?
Two-dimensional. Actually, topos is meant for three-dimensional, but millipede, that maybe we can go next day, is meant for two-dimensional analysis. I think I can show you an example. For example, how to find this is quite old, this plugin. Sika, you are Zoe, you are architect, huh? Yes? No?
I mean, it's, yeah, but I mean, it's three-dimensional, no? The thing that you showed us. It's
Yeah,
not
but how you
two-dimensional.
calculate it? Actually, I'm gonna stop sharing my screen. Stop sharing my screen. I'm gonna share a whiteboard. Where is the whiteboard? It's here. Okay. How in basic structural class, how you design a beam?
What?
This is a beam in structures. You have the supports. This is your beam. It doesn't have a mass. It's just a line. And here you have your forces that are going to be applied. The diagram of forces of this is this on momentum and this in cutting.
Are you showing us something?
Yeah, you don't see the whiteboard?
No.
No.
I see nothing.
Now you see it?
No.
No.
Oh my God, what? I'm drawing like an idiot. Okay, whiteboard. You don't really see on a whiteboard?
No.
Nope.
Oh my
Maybe
God.
it's because of Zoom. It's not loading.
Okay, let me share my screen and I do it in Paint. Or I think I have a model of millipede assembled. Let me see. Let me look for it. I think I have it. No, I don't have it. I will draw in Paint. You see my screen now? Yes, no?
Yes.
Okay. Okay, Paint. So a beam is like this, no? This is a simple beam. So you can make a topological analysis of this, but instead of drawing a line, you design a rectangle and you design another rectangle that this is the support and this is the load. And the program, instead of giving you voxels, is not giving you pixels because it doesn't need, it's going to give you stress lines. It's only something like this for a simple beam. If you have the lines, actually, just by having lines, you can automatically 3D print them. You don't even need to build the surface. But if you want, what you can do is use Dendro or other mesh software to actually make volume out of these lines. And after you can slice it with a traditional slicer like Cura. I think this is not that clear. So I'm going to try to find the millipede example. I see you are writing in the chat. I don't see the chat. So many windows open. Oh my God. Slides for a new turtle. Okay, I don't know why I'm looking for the chat. We're printing test. I think I will have to show you next day, guys. Is application documents, quarantine, millipellets, GRBL to syringe, monolith, stallion to clean. Actually, no, I think I have it here. You are lucky. Let's see if it doesn't crash. Almost crashing. This is the 3D printed part. Actually, this is the shape that I just showed you for 3D printing. That was being one. Crash it. Don't worry, let's open a new one. I have it here. I know what it is. Awesome paint. Okay, Grasshopper. Oh my God. Close and close all the errors. Okay, Grasshopper is here. Untitled 3D printing, topos, untitled. Open file. This is not what I want to show you. It's opening. No, actually it's not here. Don't know why. I'm sorry, guys. I don't know what it is. I will try to find for next day all the examples of millipede. Okay?
Okay.
Thank you very much, Edu.
Sorry for keep you waiting.
No, no problem.
Okay. Well, do you
Are
have...
you gonna upload the examples that we did in our webpage?
They are already there.
Ah, okay.
Okay.
Faster than light.
Yes. Clubs, make club, Grasshopper class. Here, download zip for folders. Sorry, I need to clean up a little bit the page, but it's here. It's a zip folder with all of them. I will also state each one individually, but Marco last time had a lot of problems to download, so I just make a zip folder for today.
Perfect.
Actually, for example, if you want to look at Amoeba, you see it looks, this is bidimensional. Oh my God, I just was here. So basically you do it with images, and this case is doing with just two-dimensional pixels. And you can just produce, if you have this is basically a PNG. Amoeba does with PNGs, for example, with images, other programs does with lines. Millipede does with lines. So in this case, for example, you can take out this and produce the cutouts. So for example, this is bidimensional analysis for CNC machining.
Mm-hmm.
I think in the MRAC this year, they also did a three-dimensional beam, CNC milled, but they used the robot to actually cut in the inner holes. And they couldn't do, of course, all the halls, but they reached a lot of places.
Mhm.
So for example, this is a building structure of stairs taking out a lot of material. Well, like this, there are millions of examples. This is bidimensional one. And some...
Am I the
some-
only one not seeing the screen now? Sorry. Are you sharing a screen?
Oh, I wish, oh my God, why didn't you...
No, you sure?
Really, guys? Really, you didn't say anything? Okay, this is bidimensional. Now you see the screen?
Yes.
Yes.
Okay, now this is bidimensional. For example, this, it produces the PNG, again I will repeat myself. And you can produce the contour extraction and take out the vectors, for example, with Amoeba, and produce the optimized legs. This is for a stair. Amoeba is good in a point that is super easy to use. Like to get something is really fast with Amoeba. To know exactly what you're doing, maybe not that fast. And you need to be logged in with an account because they need to give you an API key to actually get inside. So for example, this is a pillar topological analysis in 2D. And as you see, I choose Topos because I think it's more simple, but all the programs work really, really similar. So for example, you have supports. In Topos, all the supports are always fixed, but in Amoeba and Millipede, they can move in X or Y, or you can constrain both. The loads, you have loads, standard loads. You have tolerance. It means if you can make sharp turns or not. In other programs, these numbers are defined by Poisson model. In here, no. And you have the material parameters. That usually is a Young modulus, and depends on the program. They have other ones. You have definition of the material and a model to assemble. Most of these programs work really, really similar. So you remember before that with Topos, we have the vector of forces. In here, you have the principal stresses that you can see through lines, in this case of Amoeba, they show with colors. So it's simpler to understand if you don't have so much structural knowledge. And they do the material interaction and the percentage of material that has been cut out. So they show it's slightly more user-friendly, I can state. And it's here, the link that you didn't submit for is in the class link. So now, after making the ridiculous for the 20th time of the day, I can say that this session is over.
Yes.